So our theory of things that are small is called quantum mechanics, and it's the theory of how fundamental particles, protons, electrons, and the things we make out of them, like atoms, how they all interact with each other. And for those kinds of objects, usually gravity is not very important, because gravity is just a very weak force. The whole Earth is pulling us down in this room, so we feel like gravity is a strong force. But the gravitational force in between you and I is negligible. It's easily overpowered by the friction of me sitting on this chair. But there are regimes where quantum mechanics and gravity are both important. And the two that we tend to think about the most are in the centers of black holes and in the early universe. And black holes is more what I work on these days. So black holes are really remarkable objects where you have an object where the density of the object is so high that the gravity that it produces near it is so strong that even something that moves at the speed of light cannot escape from it. It's interesting that when you try to combine quantum mechanics and gravity, they don't fit together very well. And really, there are simple ways to see that. You just kind of try to follow your nose and combine them and see what happens. And the equations seem to look like they don't make too much sense. And at first, you don't really know why. It's just, okay, what's so different about gravity compared to, say, the electromagnetic force, which was combined with quantum mechanics 80 years ago. And really, when you think about it long enough, really the difference is that there are black holes. There are these objects where this force of gravity is so strong that nothing can escape. And when you try to combine that with quantum mechanics, it just leads to all sorts of interesting little paradoxes, which we're trying to understand using whatever tools that we can. And the thing which I personally have been involved with in that regard is what, at least to me, was at first a rather surprising development, which is that ideas from computer science, and especially ideas from quantum computer science, which is the theory of quantum computers, seem to be very useful in thinking about black holes. And in particular, there were little puzzles that we found, things where somehow we convinced ourselves that if quantum gravity is going to make any sense at all, it's going to have to be working in this kind of funny way. And I thought, that sounds familiar. This funny way that gravity seems to be working, and I thought about it, and I realized that it sounded familiar because I'd heard similar things when I was learning, just basically for fun, about how quantum computers work. And what we realized was that the mathematics which are used by people who are trying to think about what you would do with a quantum computer if you had one was mathematics which was really also useful for solving this problem in quantum gravity. And in fact, the equations were the same. This problem that nature had to somehow solve in order to make quantum gravity work was a problem that anyone who wants to build a quantum computer also has to solve. And from that point of view, it's easy to say what the problem is. The problem is that when you have a quantum computer, you need to protect the information in the memory of the quantum computer from outside interference. And actually, that's true for classical computers too. But for classical computers, we're really able to minimize the outside interference to the point where we almost don't have to do anything at this point. In early classical computers, people had to worry more about being protected from interference. But with quantum computers, it's much, much harder, because the whole point of a quantum computer is that you have a memory which you're trying to preserve in a coherent quantum state. A state that knows the difference between a qubit, which is a quantum version of a bit. So a classical bit, it's 0 or 1. A qubit could also be 0 or 1, but it could also be 0 plus 1, or 0 minus 1, or 0 plus square root of minus 1 times 1, or 0 minus square root of minus 1 times 1. And that information, whether it's plus one or minus one, is very hard to protect. The slightest interaction with the other stuff in the room will disrupt it. And so to defend against that, physicists in the mid-1990s invented something called quantum error correction, which is all about how do you protect the information in your quantum memory against errors that come, because some photon in your lab just bounced off of the memory. And so there's a whole elaborate theory of how to store the information in a way that it's redundantly protected. And what we realized is that quantum gravity also needs to do that. And it's because of the physics of black holes that it needs to do it.